Okay, anybody have any homework questions? All right, let's start with an example problem using the particle statics and the joints that we've talked about so far. And that'll sort of lead into the next thing, which is using reduced row echelon form to solve big systems of equations. Well, reduced row echelon form is just one way to do it, but all of your calculators and stuff do that. If you know of another way to solve big systems of equations on your calculator, feel free to keep using it. All right, so here's the example problem. We have a ramp that makes an angle of 20 degrees with the horizontal. And a pulley that connects a 5 kilogram block on this side with a 1 kilogram mass hanging on the other side. There's friction at the contact between the 5 kilogram block and the ramp. And we want to know what are the external forces acting on each of these two masses. I'm just going to isolate each one of these masses in turn, and I'm going to use Newton's second law for each one. So for each one, we're going to get 2 equations. We'll have a total of 4 equations that we can use to solve for 4 variables. So by the time we've written out all the variables, we'll have a sense of our chances of solving this. When I isolate the block that's on the incline, so this has friction. When you did problems like this in Physics 1, you would choose a rotated coordinate system, and so that you had the y-axis pointing out of the incline. We don't have to do that in statics. And the reason is that we're almost always dealing with static friction. And static friction, that coefficient times the normal force, only gives you an upper limit on the static friction. Well, if we're in a static case, it's very unlikely that we're at the limit. And so breaking things up into coefficients and normal forces and all that stuff, it doesn't do us any good. Okay, so when we see friction contact, we're going to keep whatever coordinate system we would have used otherwise and just treat that as an unknown force vector. Okay, that's, I talked about that last time, but that's why we're not going to, in this class, ever break things down into normal forces and coefficient times normal. All right, so let's start with the hanging mass, I guess. So a free body diagram of the 1 kilogram mass. We have a weight force acting down. That's 1 times 9.81, so 9.81 newtons. And the cable force is parallel to the cable, away from the chosen body, so this way. And I'll call that T. and I'll write out Newton's second law. This system is in static equilibrium. Everything's at rest, so there's no acceleration. So Newton's second law says we have 0, negative 9.81. That weight force is in the negative y direction. If I didn't write this, but I'm just going to use a coordinate system like this for the whole thing. And then the cable force is in the positive y direction, so 0, positive t. And that's equal to 0, 0. So we have two equations, one from the x components and one from the y components. The x components don't give us anything useful, but the y components do tell us that t is equal to 9.81. So we already know this. By the way, as an aside, if this wasn't in static equilibrium, say that there was no friction on that 5 kilogram block, this system would be accelerating. And I mean, notice it comes out to be a pretty simple answer for the tension in this cable. The tension in that cable is just caused by the weight of that mass, right? But you can't assume that in general. If this system was accelerating, that would not be the case. Okay, that the tension in that cable would be, well, depending on what that was doing, I guess. But it wouldn't in general be the weight of that mass. Okay, so now we'll go to the free body diagram of the block. Free body diagram of the 5 kilogram. We have a weight force of 5 times 9.81, so 49.05. We have a friction contact with the ramp, and so that's an unknown force direction, so I'm just going to draw x and y components of this force vector, and I'm going to give that a vector label. You could call that R, whatever. I'm going to use the subscript notation. So it's the force on the 5 kilogram by the incline. And then the last force acting on it is the cable force. That's parallel to the cable, away from the chosen body. And it's the same cable that was attached to the hanging mass, just going through a pulley. So we know that this has the same tension. And we already solved for that, so it's 9.81. So Newton's second law says 0, negative 49.05. Plus F 5I x and y components plus, so now we have to figure out the angle of this cable force. That's parallel to the incline, and the incline is at 20 degrees with the horizontal, so we know that this is at 20 degrees above the horizontal. So if you think of starting at the positive x-axis and then rotating counterclockwise to that, it's just going to be cosine and sine of 20 degrees. So 9.81 times cosine of 20, 9.81 times sine of 20. That's all the forces, and it's at rest, so the accelerations are 0. So that's Newton's second law. So we have two equations, F5ix plus, this comes out to be 9.22 is equal to 0. And the second equation, negative 49.05 plus F5iy plus 9.81 times sine of 20 comes out to be 3.36. Solve for both of those components and you get that the force vector F5i is equal to negative 9.22 for the x component, positive 45.69 for the y component. And this is in newtons. We want to calculate the external loads on both of these bodies. So we can go back to the free body diagram now and plug in these things we just calculated. So free body diagram of the 1 kilogram. There's a downward force of 9.81 and an upward force of 9.81. And free body diagram of the 5 kilogram. There's a downward weight force of 49.05. A force vector at the bottom with components negative 9.22, positive 45.69. And then a force from the cable of 9.81. Any questions about that? Okay, in this case, this is the first full problem we've done where we have multiple bodies. We're going to deal with lots of problems with multiple bodies in this class. And in this one, it turned out to be pretty easy to deal with these multiple bodies because the first one we isolated, let us solve for something on its own, and then we could plug that into the second one. But that's definitely not always the case. You can't always solve for variables using one body and then piggyback that to the next one. In most of the cases that we do, what you're gonna end up with an equation where you can't solve for a variable here, and you're just gonna have to carry this equation on as you go. And in the end, you can end up with 20 equations or something with 20 variables you want to solve for. Okay, that's gonna happen pretty regularly. I mean, 20 is pretty high, but you can end up with a lot more than that if you do more complicated problems. So we're not going to want to depend on substitution to solve systems of equations. You don't want to do substitution with 20 equations, 20 variables. And so the next thing I'm going to talk about is reduced row echelon form. And this is something all your calculators do. It's something you can do in Wolfram Alpha, MATLAB. So this is a way you always have something in your pocket that'll let you solve big systems of equations. And like I said, I'm going to talk about this one because it's the one thing that everything does, but some of you have calculators or software, whatever, that other ways, and that's fine. You just need a way to solve big systems of equations that's not substitution. Okay. So solving big systems of linear equations. Reduced row echelon form. RREF. And I'm just going to demonstrate how to do this, how you set it up so you can plug it into your calculator or whatever. And I'm going to do it with this example. This is just 3 equations for 3 variables, but you do it the same way for 20. So let's say that our system is x plus y plus z is equal to 10. Negative 2x minus z is equal to 5. And negative y plus 5z is equal to negative 10. Okay, so this is 3 linear equations for 3 variables. It's linear because we don't have any cosine of x or x squared or anything like that. All the variables we're trying to solve for appear linear with only constant coefficients. Okay. So the first step is you're going to create, it's called an augmented matrix. For this system of equations. So to do that, get all the variables on the left side of the equation and all the constants on the right side. Then, for a system of n variables and n equations, you're going to create a matrix of coefficients with n rows and n plus 1 columns. Okay, so here's how we're going to do this. So n rows, n plus 1 columns. We have 3 equations and 3 variables in our example. So we're going to have 3 rows, 4 columns. Okay. The columns represent the rows represent the equations. So that's equation 1, 2, and 3. The columns represent the variables, and you can do them in any order, but once you choose the order, it has to stay consistent. So let's say this is going to be the coefficients of x, this is going to be the coefficients of y, coefficients of z, and then this is going to be the constants. Remember, the constants are on the other side of the equation. Okay, if you don't do that, you get backwards answers. So now let's go up to the equation and come up with the coefficients of all of these. So equation 1, the coefficient of x is 1, the coefficient of y is 1, the coefficient of z is 1, and the constant is 10. Okay, any questions about that? So this is going to be 1, 1, 1, 10. And now we'll go to the second equation. The coefficient of x is -2. The coefficient of y is 0. Yep. Coefficient of z is -1. And the constant is 5. So fill this out as -2, 0, -1. What was it? -5? Positive? Yeah. And then the last one, the coefficient of x is 0, y is -1, z is 5, constant is -10. I already forgot. 0, -1, 5, -10. 0, -1, 5, -10. Okay, so that's your augmented matrix. And that's the matrix that you're going to enter into whatever program you're using. Excel will do this. Any TI calculator will do this. I think every TI calculator, at least most. And now, if we call this matrix M, okay, now just in whatever program you're using, you're going to call RREF. That's the name of this function in almost anything. And what it's going to give you is a matrix back that's also 3 by 4. And the first 3 by 3 of that matrix is going to be 1s and 0s. That doesn't do much for you, but that's just the way the algorithm works. And the last column is what you really want, and that is going to give you the answers in the order that you defined your variables. So in this case, that's -2.7, positive 12.3, and 0.45. The order that we defined these variables was x first, y second, and z third. So that's how they appear just now in a column instead of in a row. Okay. Yes?
Where did you find this on TI-84? Yeah, I see them. Oh, wait, yeah, you're right. There it is.
Okay, great. All right, so let's use this in a problem where we need to solve a system of equations. Oh, and also, I think it's the case that it tells you how to do this on every TI calculator, plus Wolfram Alpha, plus some other stuff in the text that's in D2L. It's in one of the appendices, I think, but if you're looking for it, you can find that, I think. Okay, so let's say we have this incline. And And again, there's a pulley there. This time, the cable goes over the pulley and just attaches to the ground. And the other end of the cable connects to a cart with a mass of 1 kilogram. And then another cable, a separate cable, leaves the back of the 1 kilogram cart and attaches to a 3 kilogram cart. And sitting on top of the 3 kilogram cart is a 2 kilogram mass. And there's friction at the contact between the 2 and 3 kilograms. And we want to calculate the external loads on each of these masses. And again, I'm going to just use the usual coordinate system. All right, so what we're going to do is just draw free body diagrams of each one of these masses, do Newton's second law, because we're dealing with these as particles. We're not dealing with lengths. We're not dealing with changes in orientation. And so we're going to have 2 equations from Newton's second law for the 1 kilogram, 2 for the 3 kilogram, 2 for the 2 kilogram. So that's 6 total equations. We'll be able to solve for 6 variables. And so let's do it that way. So first, I'll do a free body diagram of the 1 kilogram cart. I think actually looking at it, I wouldn't be too surprised if you did this in the other, it looks to me like if you did it in the other order, you'd be able to just do it all as you went. You wouldn't have to solve this system of equations. But I'm going to do it this way to show like you don't have to think about it. Just use the tools and it'll all work, you know. And also because when I made this problem, I might not have noticed that. Okay, so here's the 1 kilogram mass. Oh, I didn't give the angle. We need an angle for this. So let's say this is 30 degrees. Okay, we have a weight force of 1 times 9.81. Wheels make a frictionless contact with the ground. And so the rule is that force is perpendicular to the surface of contact toward the chosen body. So this way. I'll call that N1. Then here we have a cable tension. I'll call that T1. It's parallel to the cable, away from the chosen body. And then on the other side, same thing, parallel to this cable, away from the chosen body. And we'll call that T2. 3 of these forces are at funny angles, so we need to figure out how to represent those. We're going to need to do that, we're going to need to know what angle to use cosine and sine for. So let's think through that. So here's how I'm going to do it. And this isn't the only way, but this is how I'm going to do it. I'm going to draw a vector that's parallel to the incline this way. And we know that this angle is 30 degrees. That is the direction of that force T1. So when we know the counterclockwise angle from the positive x-axis here, that's going to give us our force for T1. T2 is 180 degrees from that. And the normal force is 90 degrees from either one of those. Okay. So the angles of those 3 forces are, well, to get from the x-axis to this one, what's that counterclockwise angle for this one? 150, yep. So for T1, theta is 150. For T2, we can start with that 150 and then add or subtract 180 degrees from that. I'll subtract 180, and so you get negative 30. And then for the normal force N1, um, 150. The way I have it drawn, you have to go clockwise 90 degrees, and so that's minus 90, and so that's positive 60 degrees. Any questions about that? So Newton's second law says T1 times cosine and sine of 150 plus N1 times cosine and sine of 60 plus T2 times cosine and sine of negative 30 plus 0, negative 9.81 is equal to zeros. So that is negative 0.866 T1. I'm going to split this up into the 2 equations, I guess. So negative 0.866 T1 plus 0.5 N1 plus 0.866 T2 is equal to 0. And the second equation says positive 0.5 T1 plus positive 0.866 N1 minus 0.5 T2 minus 9.81 is equal to 0. I'll just move that to the other side now because we know we have to do that for reduced row echelon form anyways. And these are our first two equations. There's one, there's two. You can't solve for either of those yet, but we'll just come back to them after we come up with all 6 equations and just make the augmented matrix and solve it that way. Okay? Any questions? Okay, so now let's go to the 3 kilogram cart. There's a weight force of 3 times 9.81, so 29.43. There's a frictionless contact at the wheels. I'll call that N2. There's the cable force that we already have a name for, that's T2. And then there's a friction contact applied to the 3 by the 2, so I'll call that the force on 3 by 2, and it's a vector. We don't know the direction. So Newton's second law says that T2, you can see that angle is going to be 150 degrees again. But if you don't see that, then you can go back and do it this way again, draw the coordinate system, draw a vector parallel to the surface, and work your way around. So this is T2 times cosine and sine of 150. N2, that's going to be 60 degrees again. So plus N2 times cosine and sine of 60. Plus F32 plus 0, negative 29.43 is equal to zeros. So that says negative 0.866 T2 plus 0.5 N2 plus F32X is equal to 0. And the Y equation says positive 0.5 T2 plus 0.866 N2 plus F32Y is equal to, get the constant on the other side, positive 29.43. These are equations 3 and 4. and you can't solve these, and you can't solve it as a system yet because we have, how many variables do we have so far? 1, 2, 3, 4, 5, 6. So we have 4 equations, 6 variables. We can't solve it yet. But if our next 2 equations, we don't put in any more variables, then we can solve it. We'll have 6 and 6. Okay? And then the last one is the 2 kilogram. There's a weight force of 2 times 9.81, so 19.62. And then there's the force on 2 by 3. We already have the force on 3 by 2. So we don't want to put this in like this. That would be 2 more variables, but we can use Newton's third law, and this is negative F32. So we haven't introduced any new variables. We're going to come up with our 5th and 6th equations, and that means we can solve this, unless some of those equations are linear multiples of other equations. Okay, so Newton's second law says 0, negative 19.62 plus negative F32x, negative F32y is equal to zeros. And this tells us that negative F32x is equal to 0, and negative F32y is equal to positive 19.62. That's our 5th and 6th equation. And our variables, what do we have? T1, N1, T2, N2, F32X, and F32Y. So there's 6 variables, 6 equations. So the augmented matrix is going to have 6 rows, 7 columns. Okay, this is equation 1, 2, 3, 4, 5, 6. The variables are T1, N1, T2, N2, F32X, F32Y, and then the constants. So equation 1, we have, actually, can someone just read these out to me? tell me the coefficients of these variables as I go through. So from equation 1, what's the coefficient of T1? Okay. N1? Okay. T2? Okay. N2? 0. Okay. And then constant? Yeah, 0. Okay. And then equation 2, T1? N1? T2? N2? 0, 0, 0. Okay. 9.81. Okay, equation 3. T1? Okay. N1, 0. T2? N2? F32X? 1 and 1. And then constant? 0. Thank you. Yep. Okay, equation 4, 0 T1, 0 N1, T2, N2, F32X is 0, F32Y is 1, and constant? 29.43. Okay, and then equation 5, it's all zeros until F32, right? Okay, -1, 0, 0. And then equation 6, all zeros until the y, and that's -1, and then 19.62. Okay, so there's the augmented matrix, and if you plug that into your calculator and do reduced row echelon form, in the first 6 by 6 matrix, you'll get just ones on the diagonal and zeros everywhere else. And these will be in the order T1, N1, T2, N2, F32X, F32Y. And so they'll come out as 29.43, 8.50, 24.53, 42.48, 0, and -19.62. Any questions about that? And so we're out of time. I'm not going to draw it, but you can imagine if you, like later on in the class, this will be a starting point for us is to get the external loads on these bodies. So now you could plug these back into the free body diagrams. You have all the external loads, and then you can use that for whatever you're doing next, trying to figure out if this thing's going to break or whatever. Okay, see you Friday. If I do want you to draw it out, I'll tell you. Usually no, but I might every once in a while just to remind you that that's what we're sort of getting at, you know.